Thank you. I'll begin with a word of prayer. Dear Father, we thank you for this day. We thank you for the break, which is about to start. Just give us the energy to finish this class and to accomplish as much as we can in the time we have. We just, again, Lord, I just pray you continue to encourage these students. If they don't feel like they're doing well, do encourage them to find what it is they can do to study better and obtain more information from their time. In my prayer, Lord Jesus. Amen. So your score means nothing. Don't look at it. We'll talk about that at the end, okay? So we're studying, again, an endomorphism. Our object of study right now is linear transformation T from a vector space V to a vector space V. Again, V is over some field F, and for the most part, we're thinking the dimension of V is equal to N. All right? And so last class, I spent considerable effort proving to you that there exists something called the minimal polynomial for T, a smallest polynomial, if you will, a degree of smallest polynomial of smallest degree, m of x, right? Smallest degree, for which what? For which, when you take that polynomial and you plug t into it, you get 0. You get the 0 transformation. So there's this minimal polynomial that exists for a transformation t. And then we also proved that I argued for you that, and I don't find a notation for this, so I'm just going to be rather clumsy and say it's the characteristic polynomial of t. And that's going to be defined to be the determinant of t minus x times the identity transformation. So this is the so-called characteristic polynomial. And the characteristic polynomial, all right, well, in particular, a 0 of the characteristic polynomial of t, in other words, you're looking for something like car t of alpha equals to 0. Well, that's just another way of saying what? The determinant of t minus alpha times I is equal to 0. Well, such a value, alpha, is known a characteristic or eigenvalue. Eigenvalue of t. It's going to turn out that if you take this characteristic polynomial, right, and so let me just, fun fact from the future. Not too far future, though. If you calculate the characteristic polynomial of t, and then you plug t into it, well, guess what? You get 0. This little fact is known as the Cayley-Hamilton theorem. One of those things I'm hoping to prove in here, all right? All right, but then getting back to the story here, eigenvectors and eigenvalues, right? So let's see here. So if there exists a v not equal to 0, such that t of v is equal to alpha v for some alpha in the field, then we say v is an eigenvector belonging to eigenvalue alpha. Okay. So our hope, right, is that these, see, because if you look at it, like the things I'm writing on the board right now, these are pretty generically true. I mean, if you think about a linear transformation, these are things we could try to calculate for the transformation, and pretty generally so. I mean, can you calculate the determinant of t minus xi? I mean, yeah, you can do that for an arbitrary polynomial. And if you believe this Cayley-Hamilton theorem, well, that's pretty cool, because that means that this characteristic polynomial is one for which when you plug in t, you get 0, right? Which means what? That means that the minimal polynomial has to divide this thing. So the minimal polynomial has to appear as basically factors inside the characteristic polynomial. And so you see there's some way forward that's a rather general story we can tell. That's the story I'm trying to tell, bit by bit. So I'm just giving you a few comments from the future here. Let me get back to the task at hand, though. We're in the invariant subspace section. Pretty much is, I don't know, I kind of want to stop and give you an example before I go further. Let's try to understand what an eigenvector and an eigenvalue is a little bit better before I go on. So I can talk about eigenvector and eigenvalue for a linear transformation, but the same definition goes through for a matrix, all right? So I'm going to give you an example. So here's the example. Okay, so if we let a equals to, let's say 0, 1, minus 1, 0. So this would be like the matrix corresponding to the transformation t of x comma y equals to, what would it be, like y comma minus x. This would be the matrix of the linear transformation from R2 to R2, all right? If you want me to tell you what this is geometrically, it's just what this thing does is it takes in a point, right? You feed it a point like a comma b, what's it do? It takes a, b, and flips them and puts a minus on the x. What does that mean? Let's see, for that point, where would that be geometrically? Yeah, second quadrant. It's, well, I don't know about that. I think it's in the fourth quadrant, actually. It's about where so we go as much over, we go down. So it's like here, and then, so it's like something like over here, I guess, right? Now, if I had done this if my picture was more to scale, I guess it's more kind of down here. What you'd see is you're going from here over to this guy. If I drew it better, you'd see that the length of that arrow is maintained. And all this really is a rotation by 90 degrees in the clockwise direction. So this linear transformation is what's called a rotation. It's a rotation by 90 degrees, in fact. So it's nothing terribly unfamiliar. Anyway, here's its matrix, and we can analyze the characteristic equation by looking at the matrix. So let's look at the characteristic. What is the characteristic polynomial for A? So that would be the determinant of, and we do, right, we do basically, oh man. No, it's fine, A minus, just a moment of stupidity. So A minus, and then we have x0, 0x, right? That's x times I. So what's that look like? Okay, that's the determinant of minus x, 1, minus 1, minus x. All right. So what's that? That's equal to x squared plus 1. So the characteristic polynomial, all right, of this matrix, or correspondingly that transformation, they have the same, the matrix and the transformation will have the same characteristic polynomial because of how the determinant works. And so the question then I have for you guys is, are there any characteristic values here? Kind of a loaded question. It depends on what I mean. Well, I guess the answer is clearly no, because I told you up here, right? So this says that T is what? T is a linear transformation on what? Yeah. R2, and R2 is a real vector space, right? So does this have any real solution? If you set this equal to 0, there are no real solutions, right? So not every matrix has a characteristic value. What happens if you plug in the matrix into this, though? Let's do that. It's kind of fun. Characteristic of A is what? That would be A squared plus 1 plus the identity matrix, right? How does that work out? What happens when you square A? What do you get? That squares to minus the identity, right? So when you plug in A into the characteristic polynomial, what do you get? You get 0. This, my friends, is the Cayley-Hamilton theorem in action. Okay. In fact, you can prove that in this case, the minimal polynomial for A is in fact equal to the characteristic polynomial of A. That's the smallest degree polynomial that you could find that when you plug in the matrix, you get 0. There's no way to take a linear polynomial in X and get that to happen. Or is there? I don't think so. Well, I don't think so. No. Pretty sure no. All right. But what would happen if instead of looking at this as a real transformation, what if we said T is the same formula, right? But it's a mapping from C2 to C2, right? Same, We also get the characteristic polynomial of, the matrix of, here again, the matrix of T is the same one, right? And so the characteristic polynomial of A still works out to x squared plus 1, but this time we can factor. It's x plus I times x minus I, right? So this has eigenvalues, let's say alpha equals to plus or minus I. Same formula, right? Different choice of field, basically. All of a sudden we have eigenvalues, whereas we didn't before. And that's the beauty of the complex numbers, right? If you look at think about this. If I have a characteristic polynomial and I'm looking for solutions in the complex numbers, well, what is a characteristic polynomial? It's nothing more than an nth order polynomial. When are there solutions to an nth order polynomial equations over the complex numbers? It's a very boring question. The answer is always, right? Because the complex numbers are algebraically closed, so there's always eigenvalues if you're looking at a complex linear transformation. So that's kind of nice. So the context matters, right? You can have the same formula if you have different choices of base field. You may or may not be able to find characteristic values. Okay. Let's move along here. I just wanted to give you that example. Oh, what are the eigenvectors here? How would you find them? You'd be looking to solve what? A minus II times like a vector, let's say V equals to 0. That would give you an eigenvector V with eigenvalue I. What's that equation? This equation is minus I, 1 minus 1 minus I. Let's say that V vector. I usually use like U and V as disposable variables for these sorts of problems. So let's see, the first equation gives me what? Minus IU plus V equals to 0. The second equation gives me what? It gives me minus U minus IV equals to 0. But look at these two equations. What happens if you take the first equation and multiply by I? It's exactly the second equation, right? These are the same equation written twice. And if you think about it, it had better be that way. Because we're looking for an eigenvector, right? Which is supposed to be non-zero. If these were two distinct equations, if they were genuinely distinct equations, that means that there's only the zero solution. So in a 2x2 case, if you've actually found an eigenvector, and you're looking to find, if you actually find an eigenvalue for real, sorry, bad choice of words. If you found an eigenvalue in verity, then you had better find that the two equations you're looking at are really the same equation. Otherwise, you can't find a non-zero solution because you'd have a unique solution, which is 0. 0 is always there. It's homogeneous. So in other words, you can pick either one you like. I will pick number 2. Number 2 gives me that U is equal to minus IV, and then I set V equals to 1 usually, and that gives me the vector V equals to minus I1. There's a token eigenvector with eigenvalue I. I won't belabor this point. You already know how to find eigenvectors, because what is the eigenvector calculation? It's the null space calculation, right? You're finding the null space of a matrix, just a particular kind of matrix. The thing that's tricky, perhaps, and new, is that to find the eigenvalues, right? To find the eigenvalues, you have to do what? You have to solve the characteristic equation. In other words, you have to find the zeros of the characteristic polynomial, right? And so this is kind of a scary thing in general, because this is an nth order polynomial equation, which might be unpleasant to really try to solve for bigger examples, right? Okay. Now, we're in section 23 basically here. Was there a question? There might have been a question that I just glossed over. Oh, you take it back? Okay. Just retracts his question. I'll allow it. Invariant subspaces. So section 23. Try to move on here. So here's the deal. Definition. If we have W is a subspace of V, and if you have T of W is a subset of W once more, then W is a T invariant subspace. I mean, I put subset here on purpose because that's all I want us to be obligated to check. But logically speaking, of course, you can easily argue that T of V is a subspace of W for what it's worth, right? I mean, how's that go? Well, if T of W is a subset of W, then that means that T restricted to W as a mapping from W to W makes sense, right? And then the range theorem takes over, right? So like T restricted to W of W is then a subspace of W, since the range is a subspace of the codomain, but the codomain here is W. So, I mean, in fact, what I'm trying to say is you could replace this subset with like less than or equal to say it's actually a subspace if you wanted to. We don't want to because we don't want to be obligated to check it's a subspace every time we do this, okay? So we'll not do that. I'm just saying that's not, it's a lazy definition. It's not as greedy as it could be. All right, Now there's a lemma here. This lemma is just nuts. Lemma 23.2. It's just fantastic. All right. So if you have T, a endomorphism, a linear transformation from V to V. Okay. And if you have a polynomial, f of x, over your field, then if you look at the kernel of f of t is t invariant. In other words, a simple way of constructing t invariant subspaces, all right, a simple way of constructing t invariant subspaces is simply to look at the kernel of various polynomials. Okay? Of course, we have some very special polynomials in mind, right? But let me show you the proof. It's really pretty and easy to understand, actually. So if, let's say, V is an element of the kernel of f of t, what's that mean? What's that mean? If we take f of t, right, and we act on V, what happens? To say V is in the kernel of f of t means that when f of t acts on V, it gives you 0. It's the definition of kernel. Consider. If we look at f of t acting on tv, right, that's f of t times t, all of that acting on v. This is how polynomials are composed with transformations, right? But t, as a transformation, commutes with f of t, right? Because f of t is a polynomial in t. It's made of constants, and like t, and then t squared, and then t cubed, and all of those different things commute with t. So you can switch the order of t and f of t. All right, this is by a lemma of a previous section that I did not prove. Sorry. And that is t of f of t of v. But what is f? F of t of v is what? It's 0, right? Remember? So this is t of 0. And we know from day one on linear transformations that linear transformations send 0 to 0. What does this calculation show? So what this shows us, right, is that t of v is an element of the kernel of f of t. Where was v? Where did v come from? V came from the kernel of f of t, right? So what does this actually show? This actually shows that this shows that the t of the kernel of f of t is a subset of the kernel of f of t. So think of this as being the w in the w invariant transformation. That shows that the kernel of f of t is in fact t invariant. What's that? is an yeah. So we're looking at T of W as a subset of W. That's what we need for T invariance of the subspace. As a simple application of this, right? If you look at the kernel of T minus alpha I is an invariant subspace. Provided what? Well, I mean, I guess provided nothing, but that's a T invariant subspace. That's true for any alpha, because T minus alpha I is a particular polynomial in T. But this is especially interesting in which case? In the case that alpha is an eigenvector, eigenvalue, right? If alpha is a characteristic value, then what does that mean? Then the dimension of this thing is greater than or equal to 1. Because there's at least one. To say alpha is an eigenvalue means there's at least one eigenvector belonging to alpha. This particular kernel has a name. This is called the eigenspace. In fact, this is called the eigenspace, corresponding to eigenvalue alpha. Yeah, I guess I could say eigenspace of alpha with respect to T. All right. Yay. At this point, the text starts talking about the direct sum decomposition of subspaces. I guess I should do that. So where we're going here is, well, I don't know. I want to go on with the text argument, right? But I kind of want to take a break here from Curtis and just show you some things which you can understand without the full-blown the theory. So I think I'm gonna kind of hit pause on Curtis right here, and so basically I'm right up to the point. The next thing we're going to do in Curtis' line of storytelling here is to study the fact that that you can look at the direct sum decomposition of a vector space, and this gives you a way of kind of breaking it up into pieces. And it's going to eventually turn out that those pieces that you're building the direct sum from are exactly these eigenspaces. The T invariance makes the matrix of a basis which is also built with respect to this direct sum decomposition particularly nice. It arranges the matrix into these blocks, which is ultimately where we're going, these block decompositions. But I think I'm going to take a step back and just talk to you about, from my heart, what's diagonalizability? Diagonalizability. Now that's not probably the right spelling. I don't know. He calls it, what does he call it? I think he calls it diagonable. Diagonable? I don't know. I don't know. Whatever. A matrix which, so here's the definition. I kind of want to take a stab at this concept for you without the full-blown machine that we're currently trying to wrap our mind around in Curtis, which is going to take significant effort, right? And I'm easily distracted, so here we go. A in Fn by n is diagonalizable when if and only if there exists P invertible such that what? P inverse AP is equal to a diagonal matrix. And I usually use lambda 1, lambda 2, lambda n. So it's 0 off the diagonal, okay? So what does this have to do with eigenvalues and eigenvectors and all that, right? Let me show you. So suppose, here's a little theorem. If A is diagonalizable, then there exist n linearly independent eigenvectors for A. Let me show how this goes. So what do we have? A is diagonalizable, right? That means that we have this P inverse AP equals to D, right? But what does that mean? That also means that we have A is equal to what? P D P inverse oh man, I think I chose the one that's hard to prove. Ah, curses. Let me leave this open here for a second. Other direction, conversely. If there exist n linearly independent eigenvectors, leave the space for that. If there exist n linearly independent eigenvectors with eigenvalues, lambda 1, lambda 2, lambda n, possibly repeated, who cares? Then, and this is for a matrix A, then A is diagonalizable. All right, this direction I think I can prove today. All right, let's try this one. So what does it mean to have linearly independent eigenvectors? It means, so assume that the matrix, if we look at the set v1, v2, vn, is linearly independent, right? That's actually a basis, right? For Fn in that case. Right, if A is an n by n matrix, I'm assuming that. I should mention that A is an element of Fn by n. Well, if this is a linearly independent set of n vectors, it's a basis. So in particular, the basis matrix beta, v1 concatenated to v2 concatenated all the way to vn, is invertible. Okay, so that's what linear independence gets us. All right? We have that. But what else do we know? We know that there exist lambda 1, lambda 2, lambda n in the field such that what? Well, A v1 equals to lambda 1 v1. That's what it means for v1 to be an eigenvector with eigenvalue lambda 1 for A. What else do we have? A v2 equals to lambda 2 v2, right? I think you see where I'm going with this. And so forth and so on, all the way out to the nth one. So if you stack these, what do you got? You've got like A times V1, V2, Vn is equal to what? So of course AV1, right? AVN, but those are what? Lambda 1 V1, lambda 2 V2, lambda n Vn, right? See, I want to find a similarity transformation, right? That moves A to a, that transforms A to a diagonal matrix. We're almost there. All we need to do is take the equation we have right there, and if you're optimistic, if you want to think of this as being the P, right? Then we should multiply this by P inverse, right? So multiply by beta inverse. So we have beta inverse A beta equals to what? Notice that beta was exactly this, the basis matrix. This is called an eigenbasis because it's a basis made of eigenvectors. So what do we have? Well, we have, we've got, you got to think about how does this work. I mean, I've got V1, V2, Vn inverse times this, lambda 1 V1, lambda 2 V2, lambda n Vn. Let me try to explain to you how that goes. So if the basis matrix inverse has, say, row 1, row 2, row n, like this, how does it work? We have basis inverse matrix times the basis, the beta. I'm missing some brackets here, aren't I? So sorry. So if we multiply the matrix inverse times the matrix, we should of course get the identity, right? But this is like row 1, row 2, row n times V1, V2, Vn equals to the identity matrix, right? What can you get from this? I mean, to try to just to explain what's the meaning of that calculation concisely, let's say this. We have that. How do you do this? You do V1. I mean, when you actually calculate this, what do you have? You've got like R1 dot V1, right? R1 dot V2 and so forth. Eventually down here you get Rn dot Vn, right? The usual matrix multiplication. Here's Rn dot V1 down here. Right, we do column times row, column times row, column times row, right? So we have, if you think about that, right, we have row I dot Vj is equal to what? Just Kronecker delta Ij, right? So write this in that notation. And work it out. What is that? Well, I mean, if you don't mind me writing it sort of all at once, this is Ri dot lambda times Vj as a matrix. That's the ijth component of it is that. But what is that? That's, pull the lambda out, and you have, well, excuse me, that's not just an arbitrary, that's lambda what? Yes, I heard it. J, yeah. So this gives us the matrix Kronecker delta Ij lambda j which is to say lambda 1, lambda 2, lambda n. So there you have it. If we have n linearly independent, right, n linearly independent eigenvectors for a matrix A, it follows that that matrix is diagonalizable. Right? Well, I mean, here's the calculation, and it's more. It's better than just that. This proof doesn't just show you that truth; it also shows you how to diagonalize it. Right? How do you diagonalize the matrix? You take the eigenbasis, right, and you similarity transform by that eigenbasis. See, by the eigenbasis inverse A eigenbasis, that diagonalizes the matrix. Can anybody tell me, given the results we've already proved in here so far, especially last class, when could we be sure that we have an eigenbasis for a matrix? I mean, that's a tough question in general. But there's some low-hanging fruit that you could pick and tell me. What did we prove last time? Last time we proved that, remember this, if you have distinct eigenvalues, you get linearly independent eigenvectors, right? So, for example, if we had a matrix A which had n distinct eigenvalues, all in the field, that would be enough to get diagonalizability. So if I have a 3 by 3 matrix and it has eigenvalues 1, 2, 3, guess what? Diagonalizable. You can diagonalize it into the form 1, 2, 3. Now you might wonder, so does that mean that if an eigenvalue is repeated, it's not diagonalizable? Nope, doesn't mean that. There are matrices with eigenvalues repeated, which are still diagonalizable. Now, there are matrices which are not diagonalizable. All right? That's the harder thing to understand. Let's see here. What do you think the odds are I can prove the other direction today? I don't know. See, he proves this in the invariant subspace section, but he uses something called the primary decomposition theorem to prove it. And I'm not entirely sure if when he does that, if he's killing a mosquito with a sledgehammer, or, if it really is a cat and it needs it. I don't know. Oh, I'm sorry. Cat lovers. I'm sorry, you guys. I don't know. I somehow have to use this. I have to somehow create eigenvectors with this equation, right? And it's easy for me to see that D has. I mean, you can see that D times E1 is equal to lambda 1 E1, right? If D is looking like this. Think about this. If you have a diagonal matrix, the eigenvectors are given to you just from the standard basis. Think about this. If you multiply this by E1, you get back lambda 1 E1, right? And if you multiply D times E2, guess what? You get lambda 2 E2. Right? So it's easy to see that a diagonal matrix has a eigenbasis, right? So in particular, and so forth. So that tells me that the standard basis even is an eigenbasis for D. But I don't need an eigenbasis for D, right? I need an eigenbasis for A. So how do I get from D to A? I suppose we. Yeah, but I need the. It's not enough to just get like linear independence. I need, I need to be able to show that A times whatever is equal to some constant times whatever whatever it was. I mean, I'm going to leave this open. I think it's good. Let you guys work on that. I want to talk to you more about examples and where we're going. Okay, I want to try to give you the big picture of what we're doing here for a little bit. So we have certain matrices which are diagonalizable, right? And some which aren't. Let me show you one that isn't. Well, I already showed you one today that isn't, didn't I? What was it? There's stuff like this, right? Not diagonalizable over the reals, right? If you look at this as a 2 by 2 real matrix, it's not diagonalizable, right? If you look at it as a 2 by 2 complex matrix, it is diagonalizable into the form I, 0, 0 minus I. But that's kind of a quirk of the field. It's not just that that's a problem. You could have something like this. 1, 2, 0, 1 is kind of a standard example. What's the characteristic equation? Well, I will degenerate back to lambda if I'm not careful. You could really use whatever variable you like here. Trying to use x to be different than my past. All right, so this is 1 minus x, 2, 0, 1 minus x. Well, that's nice. This is a triangular matrix. I just multiply the diagonals. I get x minus 1 quantity squared. I can't stomach writing 1 minus x. I'm sorry, it just bothers me. So I absorb the minus and make it x minus 1 squared. I hope that's okay. So what are the eigenvalues? We have alpha equals to 1 twice, right? You don't have, I was using alpha for eigenvalue at the moment. You could use lambda for eigenvalue. A lot of times I use lambda for eigenvalue. But, okay, what I won't do is use x for eigenvalue. Okay, so alpha equals 1 twice. What are the eigenvectors here? So we have to solve A minus what? Minus I times some vector v equals to 0. What is that? Well, that's 0, 2, 0, 0 times a vector v equals to 0. What's that tell us? What are the solutions to this? If v is equal to, v1, v2, what condition do we get? We just get 2v2 equals to 0, right? So v2 is 0, right? What about v1? v1 is free. Okay, so the kernel of A minus I, which is, by the way, the alpha equals to 1 eigenspace, is the span of what? It's just the span of 1, 0, yeah. So notice, for this matrix, there does not exist an eigenbasis. And if you believe the other half of the theorem I haven't proved, which is, this is an if and only if theorem. Basically, I'm saying A is diagonalizable if and only if there exists a basis of eigenvectors, right? So I guess by the direction I haven't proved yet, it follows that A is not diagonalizable because you simply cannot produce an eigenbasis for it, right? There's only one eigenvector to find here. Sometimes there's none. Sometimes there's 1, even when the eigenvalue was repeated. Another example, if you have this, 1, 3, 0, 0, 1. Oh, I'm sorry, I meant 3's on the diagonal. 1's on the super diagonal. And then I'll put a 3 down here. What is it? What'd I do? It's what?
My spring break has started.
Oh, your spring break started? Oh. Well, that's hardly any fun. I mean, I'm glad for your spring break, but I'm sad for my class. I'll just tell you, I won't calculate it. But this one, what's the eigen? By the way, the eigenvalues of a triangular matrix you can read from the triangle. So this has just alpha equals to 3 4 times. And in fact, I can tell from just looking at this matrix that there only exist 2 linearly independent eigenvectors. The characteristic polynomial of this will be 3 minus x, quantity to the 4th. I think the minimal polynomial here, well, I won't speculate, but once you understand this entirely, you'll be able to read the minimal polynomial off this form. This form you're looking at is the Jordan form. It's the next best thing to diagonalizability for a matrix. Anyway, we'd like to understand that more deeply, and of course we have work to do. But I guess we have a break to do first. So I'm moving the quiz back to the Monday after the Friday after.